I saw this really nice problem on Mind Your Decisions and thought I'd try and get to know the problem myself and offer a couple of calculus-free solutions, making use of the symmetries of the problem. Do head over to Mind Your Decisions and press Tawalka for a great solution to the problem. Okay, and the problem is, given a right-angled triangle with a rectangle inscribed and segments of length 3 and 4 as marked here, first of all, what is the area of the shaded rectangle? And secondly, what is the minimum area of the large triangle? And similarly to Mind Your Decisions, I will think about this straight line and think about the gradient of that straight line, admittedly perhaps going the other way to the way gradient is normally considered in coordinate geometry. So if this line has slope m, so we're going 3 across, we're going 3m up, and now how far do we need to go across the gradient of m to go 4 up? Well, that's just going to be 4 over m. Okay, so we can answer A and say that our area of our rectangle is 3m times 4 over m, which is 12. And now for part B, we can see that the area of this triangle is going to be 4 over m plus 3 as the base, times 4 plus 3m as the height of the big triangle, all times a half. So half times base times height. And tidying that up a little, I get 4 plus 3m squared over 2m. And I'm going to call that function something. I'm going to call that capital A. Okay, now obviously we could now minimize this function using the techniques from calculus, but just for fun, let's have a look without. So if I take a look at the graph of this function, it looks like this, and you can see in fact that it has rotational symmetry about the point 0, 12. Has 180 degree rotational symmetry around that point. Now how can we see that? Well, in fact we can see that by multiplying out this bracket and just rewriting that slightly. So apart from this 12, this function is odd. So if I translate this down by 12, this function becomes an odd function, and odd functions have this kind of rotational symmetry. It's 180 degree rotational symmetry. Notice though that the maximum of this part here, the maximum here occurs at this double root. And the double root, and we can see the coordinates of this double root perfectly nicely setting for us up here. So that is just minus 4 over 3, 0. And when we rotate this round, we find our minimum point up here. So 4 over 3, 24. So we'll find the gradient of that line, you remember in here, will be 4 over 3. So this is in fact going to be 4, and then this is going to be 4, and this is 3. Just as they found in Mind Your Decisions. So our minimum area here is exactly this y value, this value of a of m, which is 24. Yeah, and the other approach I thought I'd mention to solving this problem is to do with first applying some transformations to our shape. So we can first consider a horizontal stretch, or squash if you prefer, scaling this down by a factor of 3, so to turn this 3 into a 1. And now we can also imagine squashing this down by a factor of 4, so that this 4 here also becomes a 1. And now I claim that we can sort of see that the minimal configuration after we've done all this squashing is exactly the situation where I've got a 45 degree angle here, 1, 1, so there's 1s here and here. And notice in fact the numbers work out then, because my areas have all gone down by a factor of 12 here, so from here to here, divided by a factor of 12. This square here has area 1, and this triangle here has area 2. So scaling back up, this would have area 12, and the minimum area of the big triangle should be 24. And how can we see more precisely that this is the minimal configuration here? Just looking at maybe this triangle and this triangle, the areas of those two, if this has slope m, using the same trick as before, this will have height m, this will have length 1 over m, so the turquoise triangles will have total area m plus 1 over m, all divided by 2. Notice there's the square here will have area 1 no matter what the value of m is. And notice that this is symmetric in the transformation which sends m to 1 over m. Okay? And geometrically what I'm doing is taking a reflection in the 45 degree line. And that will take one of these configurations of triangles and rectangles to another one of the same area. So wherever that minimum occurs, it has to happen exactly where m is equal to 1 over m, and if we also know m is positive, that means that m has to be 1, so the gradient of this line has to be 1, so we have exactly this 45-degree configuration. So this will have to have area 2, and the whole triangle will have to have area 24. Okay, well, thank you very much for watching. I hope that was at least somewhat interesting.